Hello, my name is Angelo Naples, and I'm going to be teaching you all about temperature change and phase change. Let's begin. Say we have a problem, such as this one, where an ice block weighing at 3 kilograms has 11 million joules of energy added to it. This is done after the ice is cooled down to negative 200 degrees Celsius. What is the final temperature and final phase of the ice? So, to do that, we need to know a couple things. First off, what is a joule? Or that J term, that J at the end of 11 million in the problem. Right here. So what is a joule? A joule is the SI unit of work or energy, equal to the work done by the force of 1 Newton at the application point moves 1 meter in direction of the action of the force, equivalent to 3,600th of a watt-hour. Or, to make it easy, in our case, it's the amount of energy that is added through heat flow. What heat does to temperature? So, say you have a substance, such as water, and it's at a certain temperature, and that it's below its melting point, so it's a solid. So you take it, and you have to add some heat to it. And as you're adding heat, the temperature will rise. And then eventually, it will hit its melting point. So say it's something like chocolate. It's solid, and then eventually, after being in your mouth so long, your mouth puts heat into it, and it hits its melting point, and it begins melting. At its melting point, it does not actually get any hotter. That's why when anything melts, it will not get hotter. Or same goes when it's freezing. And then eventually, it will be completely melted and be fully a liquid. Then as you add more heat to it, it'll keep going and keep going and keep going all the way till it hits its boiling point, where it begins vaporizing. And as it's vaporizing, yet again, the temperature will not change. When an object or substance is undergoing any phase change at any of these, the temperature will not change. Eventually, it will be completely done vaporizing, and then it will be fully a gas. What is the equation for change in temperature? So, in our problem, we will need to know this equation. Q equals mc delta T. Q is the amount of heat transferred. M is the mass. C is the specific heat, and delta T is the change in temp. This equation will allow us to find out how much heat needs to be transferred to figure out what the change in temp is, or vice versa. That is because in our problem, both mass and specific heat will be constants. So, yeah. Specific heat, as I mentioned before, is the amount of heat it takes to raise 1 kilogram of a substance 1 degree, and has the following thing at the end: joules per kilogram degrees Celsius. So, for example, ice will take 2,100 joules per kilogram degrees Celsius to raise 1 kilogram 1 degree. Water has a specific heat of 4,180 joules per kilogram degrees Celsius, and steam has a specific heat of 2,000 joules per kilograms degrees Celsius. Now we have the equation of phase change. In this equation, it is Q equals mL, and Q is heat transferred still, and mass is the M still, and Q is latent heat. This equation will help us find out how much heat must be added to turn all the mass into the next phase. So, latent heat. Latent heat is the amount of heat it takes to cause 1 kilogram of the substance to undergo a phase change. So, for example, H2O, or ice, water, and steam, to melt, it will take 333,000 joules to melt 1 kilogram of ice into water. And to take water and vaporize it into steam, it'll take 2,260,000 joules per kilogram of water. Now that we know all this, we can look and analyze our problem in more detail. We know that the ice block weighs at 3 kilograms and has 11,000 joules of energy added to it. This is done when the ice is cooled down to negative 200 degrees, and what is the final temperature and final phase of the ice. So because of all the numbers that it gives us, we now know that the mass of the substance through the entire problem is 3 kilograms of H2O. We also know that the overall heat flow is 11 million joules of energy. So this is the amount of heat that we have to use. We also know that the starting temp is negative 200 degrees Celsius. This would fall in this area of our graph because we know that it's below the melting point of water. So it would become a solid, so it would be down here. So to start off our problem, we need to start off on step 1, where we take the solid, the ice, and get it up to where it will begin melting. This would mean that we take the ice and go from its starting temperature of 200 degrees Celsius and get it all the way up to 0 degrees Celsius. For this, we will use our change in temperature equation, the one from before. And we know the mass of the water is 3 kilograms, and we know that the specific heat is 2,100 joules per kilograms degrees Celsius, and we know the temperature change because we know that it starts at negative 200 and goes up to 0, meaning the difference of these two is 200, and then you do the multiplication and you get this Q value. This is the amount of heat that it will take to get the H2O from negative 200 degrees to where it will begin melting. And now that we know that, we can take this amount of energy that we used to melt it away from the 11 million joules to get the amount of joules we have remaining, which is 9,740,000 joules that remain. Step 2 is when we go from an ice object up to a liquid object. Whoops. In this process, the temperature does not change, so we now know we have to use the phase change equation, which is Q equals ml. Yet again, we know M is 3 kilograms because that will not change. And we also know that we are going from ice to water. So we also have this. This term we had before, if you remember that other slide. It is 333,000 joules per kilogram, and then you multiply them to get 999,000 joules. This is the amount of heat energy that it will take to melt 3 kilograms of ice into water. Yet again, we will take this from our previous remaining number, and we will get the new amount of energy that we have to use, which is 8,741,000 joules that remain. Step 3. We are taking this now liquid water and trying to get it all the way up to gas, at least as high as we can. So we start off with 0 degrees Celsius, which is where we were. And we want to get it up to the boiling point at 100 degrees Celsius. If you remember, that's right here. So we're going to use our change in temp equation again. We're going to plug in all our values, 3, and then instead of the 2,000 2,100, we're going to use 4,180 because that is the specific heat of water. And now we're going to use our new change in temperature, which is 100 degrees Celsius. After multiplying this equation out, we will get the Q value of 1,254 joules of energy, of heat transfer. And then you will take this away from your previous remaining to get 7,487,000 joules that remain. This now will lead us into step 4, in which we are vaporizing the water into steam. So yet again, in this process, the temperature is unchanged, so there is no delta T, but there is also no specific heat. We will have to use the latent heat. Yet again, we're going to use Q equals ml, and we're going to plug in the mass of 3 kilograms, and we're going to plug in the new specific heat, or latent heat, of 2,260,000 joules per kilogram. After multiplying this out, you will get 6,780,000 joules of heat energy it will take to vaporize the entire 3 grams of water into steam. After taking that away from the remaining heat after you get it to where it's beginning to vaporize, to where it's at 100 degrees Celsius, you will only have 707,000 joules remaining. Now with this is how much we have left. And after it hits steam, it will just keep going. So we now know that as it's in steam, this is how much energy we will have to be using. So in step 5, we're right here, turning the gas from 100 degrees into an unknown temperature. However, in this equation, we know what Q equals. Q equals this value from before, because that is how much energy we have left of that original 11 million. Also, mass is also constant, and we are now using the specific heat of steam, which is 2,000 joules per kilogram degree Celsius. Or 2,000, I mean. And this question mark here represents the final temperature of the steam, which is 117 degrees Celsius. But if you recall, that is the amount of temperature change. So you would take this and add it to your 100 degrees Celsius. So you will have 3 kilograms of water vapor and this number's wrong. Here, give me 1 second. Three, 2, 1. You will have 3 kilograms of water vapor and 217.83 degrees Celsius will be the temperature of this water vapor. And that is how you solve a problem like this one. See ya.